Okay, welcome everyone. Today we have our exciting lecturer here. Her name is Sonia Petrone. She is a professor of statistics at Bocconi University in Milan. After obtaining her PhD in statistics at the University of Trento, she has been visiting and conducting research in various universities and research institutes, such as Stanford and Cornell universities. Her work is focused on Bayesian statistics, Bayesian nonparametrics, and mixture and latent variable models. She has been the president of ISBA, International Society of Bayesian Analysis, a co-editor of Bayesian Analysis, and is the current editor of Statistical Science. Today, she will give a lecture on Bayesian prediction with streaming data. Okay, Sonia, the stage is yours.
Thank you very much, Mijong, for this nice introduction, for pronouncing perfectly all the Italian names there. So I guess I should share the screen now. Let's see, share content, screen. Oops. Here, can you see it? Can you see it?
Yes.
Yes. Okay, so I can go, I guess. So my lecture will be on Bayesian prediction with streaming data. And before I get started, let me really congratulate for this summer school from remote. I'm really impressed by the amazing job you have done and you are doing. Of course, the program is wonderful, but you are caring also so well of the networking and social aspects of the summer school that I think are also important. It's really amazing. It's being a great experience, certainly unusual, but very interesting and great. And so really congratulations and thank you for all this. Thank you very much. And also thank you for having me, a statistician, taking part of it. Let me say, can you see me and hear me well?
We can hear you well.
Okay. And so I was saying, I'm very happy to be part in this summer school. Kind of surprised because I am not a machine learning person. I'm a statistician, a Bayesian statistician. So I hope I will find the language appropriate for this crowd. But also I think that having different viewpoints and having the participants exposed to different research fields and different approaches is one of the aspects, or the features of this summer school, and which I find very good. So I hope I will be clear enough and say something of interest for you. So the title of my talk is Bayesian prediction with streaming data. So there are somehow two keywords. Bayesian prediction is the first. And so, again, I don't know how much background you student participants have on Bayesian statistics. So I apologize if I say something well known to you, but I think it's worth to start from here. No? What are, I think, the core principles?
Sonia,
yes.
Can you turn on your camera?
Let me see if I don't have the camera. Let me see. Oh, sorry. Oh, yes. There was something strange. So, and now sharing screen. I'm sharing screen. Let's see. Now, can you see me or?
Oh, this only shows the slides.
The slides, but not me. And I have no clue.
So when you share the slides, it's only the slides, not the your camera is disabled.
But I think let's say. Now I'm sure I have the video and I share the slides and I'm here. Can you see me? No, it doesn't work. I don't know. It might be the iPad giving this, so you can't see me at all.
Yeah,
that's also bothering for me. It's but I have no clue.
I guess let's go with this option.
Let's go with this. I'm sorry. Yeah. So it's strange. I was saying that the first part would be on somehow a bit of history and foundations in order to revisit with you the foundational principles of Bayesian prediction. And this part will be kind of informal and simple. In fact, not that simple, because we are trying to talk about principles, and you know, sometimes it's easier to write down some technical math than thinking about principles. But that's what I wanted to start with. And then we'll move to an example with streaming data, the second keywords of the title. So I'll move from an example on unsupervised learning and classification with streaming data and using a simple mixer model. This would be our running example. And in this example, and in fact, this is something that holds in general, we will see that the Bayesian approach gives a natural solution, in principle, a simple solution that is often optimal, but computations get immediately involved. And more so when we have streaming data and online learning. Because we don't want the computations are involved even with batch data, and we don't want to run the computations all over again as when a new observation becomes available. And so we need some faster solution that often goes in the direction of an approximate Bayesian solution. And for this specific problem, our running example, people have proposed a simple and fast recursive algorithm. We want the computations to be recursive because, as I was saying, we don't want to run all the computations again and again. Maybe some of you have heard, knows about Kalman filter. That's a typical example of a powerful recursive Bayesian solution. No? We would like to be able to update we don't want to store all the data. We just want to keep our latest forecast and then update it as a new observation becomes available. And here we will see for the specific problem, the mixer model for unsupervised learning and classification, we will see a recursive algorithm. But an algorithm gives a point forecast. And so a question is, how about uncertainty? And this is somehow the second topic of, that I would like to deal with in this lecture. And that's the general question is, how can we quantify the uncertainty on the answers provided by an algorithm? And again, in this problem, so let's say, how can we deal with uncertainty around the results of an algorithm? So as a statistician, the way I would like to propose you to address this question is to try to see if we can go from an algorithm to a statistical method. So here we go back to the predictive approach of the first point up here. In point 1, we take that predictive approach. We regard the algorithm as a probabilistic predictive rule. And in this approach, we will see that we will be able to see that the algorithm, in fact, underlies an implicit statistical model, and that will be a Bayesian, or an approximately Bayesian statistical model. And we will be able to quantify the uncertainty on the results given by the algorithm. again, that's annoying that you can't see me. Oops, sorry, it's wrong. Anyway, if there are any questions, or since we have this completely blind presentation, I guess it's better if you interrupt me and let me know, because I don't have any feedback. So let's start. The first part, Bayesian prediction, principles of Bayesian prediction. And I start even from the very beginning, the job of statistics, even beyond Bayesian statistics. Let's chat a bit together. What's what I could say is the job of statistics, and have in mind the crisis we are living for the pandemic, COVID-19. I would say I try here, I'm being a bit schematic, but maybe we can see that I can agree that here are some steps, typical steps of a statistical problem. No? COVID-19, we want to be to collaborate to the progress of medicine, in the search of a vaccine. We would need to make forecasts about the spread of contagion. We should quantify the risk and help taking decisions, should we have a lockdown or not. And so being schematically, first step is always, not only for COVID-19, talk with experts, have some knowledge of the phenomenon under study, think, and formulate questions. What are the questions, the important questions, the interesting questions for the problem? And then second step is we want to collect information, which means collecting data, sampling perhaps, but also collect information from experts. So you see, it's a patient work also. And then we have to collect the data. Organize the information, so have explored the data, set algorithms or statistical models, and so learn, could be learn about parameters, learn about the model, predict, evaluate risk. So prediction in itself is not always enough. We want to do this all for evaluating the risk of the progress of the pandemics, the pandemic, for example, evaluate risk. And we want to do this all because at the end we have to take a decision. And so our job is also to support a decision that has to be taken under incomplete information or uncertainty. There is another step that statisticians are generally not so good in doing, which is communicate this all to people, to the society. Maybe machine learning, you are better in this, I don't know. But it's of course an important step as well. So the question is, I wish we were in class and see and listen to your answers. Where does machine learning fit in these steps? Where does your work fit? I can't hear the answers. Where does Bayesian statistics fit? I would say all over in these steps. And for the beginning to discuss that better, let me zoom into these learn and predict steps. Zooming in, learning and predicting. So what's the approach in statistics? So I also would like, that's my vision of what's the approach of statistics, especially is my vision, what's the typical approach in machine learning. So you're very welcome to contradict me if it's not. In statistics, people say the emphasis is in the learning step, learning from experience, learning on the model, learning on parameters. We have a sample, say that's x1, y1, and so. We assume these are random variables coming, generated from a probabilistic model, say of data. And then we have to estimate the parameters, and then we have to predict and provide uncertainty quantification, so quantify the uncertainty around our prediction. But typically statistics is focused on the learning step more than on the prediction step. The approach in machine learning is, I would say, similar, but with more emphasis on prediction. We have a training sample as above. We have to train the algorithm, which is somehow estimate the parameters, and we want to predict. I'm not sure about quantifying the uncertainty about the results of our algorithm in machine learning, which is a main goal for a statistician. And again, I would say that classical statistics is more focused on this learning step, estimate the parameters. Machine learning is more focused on the prediction step. And Bayesian statistics is also more focused on the prediction step with uncertainty quantification. We always expressing our predictions in terms of probability, as we are going to see. So in this way, I think is much closer to an approach that I'm claiming is more typical of machine learning than of classical statistics. So let's see what is in a nutshell the core, the principles of the Bayesian approach. You know, often when I teach my students, I say, well, they want to know in 10 minutes what's Bayesian, what's the Bayesian approach. I would say that the two main principles are that incomplete information or uncertainty is formalized through probability. We describe our so probability is the way we choose for describing incomplete information. And learning, once we accept this, then what's the learning? Well, learning or predicting is solved through conditional probabilities. Learning on a parameters where we want to understand, to compute the conditional distribution of a parameter given the data, the so-called posterior distribution. Prediction, the problem of predicting the next xn plus 1 given the data, is solved by computing the predictive distribution, the conditional distribution of xn plus 1 given the data. And then that's the answer to the problem of prediction in a Bayesian approach. The predictive distribution, say the density, the predicted density gives a full description of the information that we have on the next xn plus 1 given the data. That's a full answer. We have a complete description of the information. Of course, it's not complete information. We have uncertainty. But it's a full description of our information, limited information on the next observation given the data. From the predictive density, we can compute point forecast as summaries of the predictive densities with respect to some loss function, for example, quadratic loss at the best summary. So the Bayesian forecast with respect to quadratic loss would be the posterior expectation, the conditional expectation. And we can also not only provide a point forecast, which is typically the result of an algorithm, but also provide credible intervals. So we can say, what's the probability that the next observation xn plus 1, let's see, is included in an interval. So not only a point forecast, but also credible intervals. That's a point. Do we agree on this? Is that clear? Is it unusual? It is very, very familiar. I don't see answers. Okay. Yes. Okay. So let me insist on this a moment. So we chat a bit with a little bit of history. I think it can be useful because often in statistics and perhaps also machine learning, the Bayesian approach is just regarded as another tool, yet another tool for having good estimates or possibly good forecasts. Because formally it can be proved that often has optimal properties. So I would like to insist a bit with this flash on history on the fact that, in fact, the Bayesian approach is a different approach that moves from a different interpretation on the role of probability and prediction. again, I would ask to you, do you use probability in your work? And if so, what notion of probability? If you use probability, likely you use a notion of frequentist probability, the probability as a limit of a frequency. In the Bayesian approach, probability has a different role and a different interpretation. So let me have these 3 slides of history on the origin of the modern Bayesian statistics, modern Bayesian approach. Of course, the origins go much back in the past to Bayes, Bernoulli, Laplace, and others. I'm saying modern Bayesian statistics as what was developed in the last century by people like Ramsey, De Finetti, Savage, and others. And to understand what I was mentioning above, that there is a different interpretation on the role of probability and prediction, let's think of the historical environment where these people, Ramsey, De Finetti, Savage, were living and were working. So for a moment, forget we are having a very modern, remote summer school, technological, and let's go back for a moment in the 1920s, 1950s, and think of the historical environment where these people were working. And we will see in a moment that, and perhaps it's not a coincidence, that they were not strictly statisticians, they were mathematicians, logicians, probabilists, also involved in actuarial sciences, economics, information, risk, and decision. Ramsey lived in the beginning of last century, he died very young, and so last century, we are in Europe, so at the time, Europe was the center, at least of our Western little part of the hemisphere. So imagine Europe, the UK, the British colleges, Cambridge. So Ramsey was in Cambridge, and at the time, Cambridge was a center of knowledge, and he was living there, working there with economists, whose names you might have heard, like Piero Sraffa or Keynes, and they were interested in giving foundations to rational behavior of agents, how people behave and take decisions under uncertainty, or how people should behave, agents should behave to take decisions in a condition of uncertain, incomplete information. So Ramsey was more interested in logic as the science of rational thought. And we have another giant, for me, perhaps the founder of modern Bayesian statistics, Bruno De Finetti. Bruno De Finetti is known as a probabilist, but he was also as a revolutionary viewpoints on many other problems. He studied mathematics, but then he worked as an actuarial at first. And so he was interested on actuarial problems, life insurance, mathematics, credibility theory, theory of risk. Let me mention just an anecdote. Somehow his work in the theory of risk of 1940 anticipated the work of Markowitz, for which Markowitz had the Nobel Prize in 1990. And as you cannot see, but you see the Finetti scoops Markowitz, so he acknowledged that. So you see the emphasis, oops, the emphasis, let's go back, is not on frequencies, is on insurance risk and so on. And then we have Savage. You see here is the Second World War. De Finetti was in Italy, Ramsey was in Cambridge, and now after the war, or during the war, just under the Nazis, people emigrated, people who could emigrated, ran away Europe, that was under the Nazis, and moved all over the world, but especially in the US. So you see the center now become our western part of the world was moved to the US, and Savage worked at Princeton, again with economists like von Neumann, Friedman, and Samuelson. And then we have Abraham Wahl, that also in a way had a major role in pointing at optimal properties of Bayesian solution. And so Walde was involved with the military research during the work. So you see, this was just to make your mind turning from frequencies of probability as frequencies to the problem of predicting, evaluating risk, and taking decisions. That was in the last part of my schematic vision of what's the job of a statistician, and also I think of a machine learner. So we here are trying to give an axiomatization of rational decisions. We try to found the probability in terms of as expression, as a principled way to model how agents take decisions. And in this all, anyway, I cannot go much into that, prediction as a central role. Definetti writes that we don't want to express information, probability, on events that we cannot observe, like parameters. We rather express information on facts that we can observe. And what we use as a model is just a ring of the chain from past events to the prediction of future events. And perhaps I could rephrase his words by saying the algorithm also. We don't care so much about the model. We have these complicated deep learning networks and so on. So we have an algorithm that we might not even understand fully, but we are mainly interested in prediction. But don't forget that we also want to formalize our information through probability. Any question? Mijan, give me a feedback. Can you hear me?
I think the problem is students are muted by default. So if they ask questions, they have to raise their hand, and then we have to enable them.
Okay.
Unmute and so on.
So now focus. That was in a kind of an historical background to have you in the Bayesian mood that I mean to underline. No? And then let's focus on Bayesian prediction. We said prediction as a central role. And the problem of prediction is, okay, we have data, we want to predict the next observation. This, I write X, but X could be a vector. So it could be a vector including covariates and a variable of interest Y, I'm just writing X. What's the classical the setting of prediction in classical statistics and perhaps also in machine learning? So we have a random sample, and this random sample, well, we are using probability. I'm not discussing any longer that. So the data are thought as a random sample. Xi are IID, independent and identically distributed according to some distribution indexed by some unknown parameter. That's a classical basis setting, random sampling. Observations are independent. But if they are independent, how can I solve the problem of prediction? If they are independent, xn plus 1 given the data has the same distribution as xn plus 1 because they are independent. And so I'm not learning through probability about future observations. The conditional distribution, the predictive distribution is just the distribution I started from. It's just this one. And so what people do, well, we use the training sample where we estimate the parameters, for example, by maximum likelihood, we plug them in, and we just have this as the prediction. And the Bayesian approach, no, we want to learn on future events. And so we want to formalize the fact that past events give us information about future events. And we want to do this in terms of probability. So even if we have an experiment where the data are collected in a physically independent way, we want to learn from experience. We want to learn from the past about the future. So we introduce a probabilistic dependence. Otherwise, we would be back to this situation where we actually don't learn anything because xn plus 1 doesn't depend on the past. And what is the notion in the Bayesian approach that replaces the classical notion of random sampling? It's the well-known, I think, notion of exchangeability. So we express a probability on the observables, on the observable random variables. We don't introduce parameters so far. And we say that the sequence is exchangeable, which means informally that the labels of the units do not matter. And so if we consider the joint distribution here, it's invariant under permutations of the label. And this indeed expresses a notion of sampling at random, because the label of the name of a single individual on which we observe income, for example, doesn't matter. It's the analog of random sampling. Whoop. I play with this pencil, but with not much success. And then in this probabilistic setting, because we have a probabilistic dependence among the xi's, we can solve the problem of prediction by computing the predictive distribution. And as I said, this in principle, that's the answer. We formalize the information on xn plus 1 through the predictive distribution. That is kind of a foundational story, but then how can we assign the predictive distribution? Well, again, this is a general notion. Now we use this simple setting of exchangeable observations. So random sampling, the Bayesian rephrasing, if you want, of random sampling of IID. They are not independent. There is probabilistic dependence because we learn on the future based on the past. So here are two kind of well-known properties, but important probabilistic properties of an exchangeable sequence of random variables. First fact is that the sequence of empirical distributions and the sequence of predictive distributions converge. They have a limit. And they converge to the same limit. And this is empirical distribution, the frequency, predictive distributions, xn plus 1 given the past. They converge. The limit is random, and it's a random distribution as well. It's called the directed random measurables. In Bayesian statistics, this limit is what we call the model, and its probability law is the prior. Why can I say this? Because of the Finite's representation theorem for an exchangeable sequence, which says that if xn is exchangeable, then there exists an f, and we just saw what this f is, such that it's a random distribution f, such that the xi are conditionally independent given f, and also identically distributed given f. They are IID given f according to f. What is this f? This f is the limit of the empirical distribution. So the statistic is what we call the statistical model in Bayesian statistics. And it's random, so it has a prior distribution, it has a probability law, and this is what we call the prior law on f. So how do we assign the predictive distribution? Usually we exploit this. Usually we do this. We use what is called the hypothetical approach. We give a prior on this, on the unknown limit distribution. No? So F is the limit of frequency. You see, we are Bayesian, but we care about frequencies. The statistical model is the limiting frequencies. It is the limit of frequency distribution. If we have a sample of many observations, and we would look at the empirical distribution, well, in the limit, that's the statistical model we are using. And this is unknown to us, so we give a prior. Usually we model this through a parametric model. And we have the usual setting of Bayesian inference, where this is the prior on F, but F is modeled through theta, so it's a prior on theta. Once we have this setting, the usual setting, then the predictive distribution is just computed as, in a way, is the weighted average of the possible densities indexed by theta, average with the posterior distribution of theta. I hope this is familiar to everybody. Otherwise, I think it would be not so clear, but I think it's familiar. Instead, I like to underline that we can take another approach, which I call the predictive approach. So rather than reasoning on the model and the prior on theta, we could, because we said we would like to avoid giving a probability law on unknown parameters. So let's reason on something that we can observe. Ideally, we would like to assign directly the predictive rule. We would like to say what's x1 as a distribution p1, and then for any n, give the predictive distribution pn. Why I'm mentioning this? Because in a moment, this predictive distribution will be my way to read the predictive algorithm. So this, I can think of having a predictive rule that could be an algorithm. Somebody uses an algorithm for producing forecasts. The Bayesian interpretation of this could be, well, you are giving me your predictive distribution through this predictive approach. And of course, if we follow the usual standard approach, we can go to the predictive. But it's also true that we can do the other way around. We can go the other way around. So again, from here, we can go to the predictive distribution. And now I'm saying that we can go the other way around. We can start from the predictive distribution. I'm calling it Pn. And we can deduce from the predictive distribution. We can go back and understand what's the underlying model and what's the underlying prior. We usually in statistics go this way, but it's interesting that we can also go from the predictive, we will see from an algorithm, to the implicit model and prior. There is a resulting probability that says that the sequence of predictive distribution, the sequence of predictive distributions characterizes the probability law of a process. So if I have x1, xn, I say what's the distribution of P1, and then what's the distribution of P2 given P1, and then of P3 given P1, given x1 and x2, and so on. Then I characterize the entire probability law, the probability law of the entire sequence. And if P is exchangeable, then we saw that if it is exchangeable, then there exists a model and a prior such that the xi are IID according to that model and so on. And so, and in fact, we saw something more. We saw that, oops, I would like to have the pencils again. Okay, oops. So we would, what is this model? So we give the prediction, what is the model and the prior? Well, they are given as the limits of the sequence of predictive distributions. So we can find them. And Sorry. What's happening? Okay, and this is the approach I'm going to exploit in the second part of this lecture, when we will have a recursive algorithm for Bayesian prediction with streaming data. We will regard the algorithm as a probabilistic predictive rule, and taking this approach, we will be able to see that this algorithm implies a statistical model and a prior. And why is this useful? Because then we will be able to quantify the uncertainty about the forecast provided by the algorithm. And here is the example I was mentioning. So keep in mind this, no? We said we give the sequence of predictive rules, and under exchangeability, I'm working under exchangeability here because that's the basic setting. Again, it's the analog of IID sampling. We have to understand what's happening, what is going on there before understanding more complex situations.
I have a question.
Yes, very happy to have questions.
When P is exchangeable, you have one unique pair of model and prior law?
Yes.
If P is not exchangeable, then there's no unique pair.
No, there is not, in general, no. But if it is not exchangeable, for example, if there is a time, of course, things are more flexible and more complex. But often, even in those situations, one could have forms of partial exchangeability. Markov exchangeability, partial exchangeability, row column exchangeability for graphs. So these things are more general than it may happen from this basic setting, you know. But I'm not claiming that with this approach we can solve the problem of quantifying the uncertainty of any algorithm. Of course, no. But it is a direction to explore, and it's really fits in this idea of Bayesian approach as a different way to regard probability prediction in terms of probability and conditional distributions, no? So, of course, it cannot be the solution of everything, but it is more powerful than it will appear from the simple example, from the simple framework of, apparently simple framework of exchangeability.
All right, thank you.
And it's honestly, this idea of connecting this all with algorithms is a kind of my idea on which I've been recently working. So I don't know how far we can go. I would be really curious to see. I think we can go further, but it's to be explored. Thank you very much for the question. Any other question?
Oh, there are some questions, but...
So maybe we can have, because then I'm moving on kind of a second part and then...
okay.
So, okay, let's have questions. Otherwise, I don't know if I'm speaking. I don't even see myself, which is, I'm sorry about that. Maybe I can have a questions showing my face for a moment.
Yeah, that would be good. We can have 5-minute break-ish question.
I should stop.
So this question is from...
Yes, okay.
Says, could we also say machine learning is more focused on the generalizations of models and statistics?
Say again, so if machine learning is more interested in generalizations of models?
Yeah, than statistics.
I don't know in what sense generalization of models. If you mean generalization from the training sample to the future?
Do you want to ask?
Then I would say the opposite. So generalization in the sense of having models that can treat more complex situations.
He's saying from training to future.
From training to future, I would say the other way around. Because, I mean, I tried to find the time to attend some lectures in the past days Unfortunately, I couldn't attend all. But the beginning of Niccolò Cesabianchi lecture, for example, he was saying the setting is IID, which is very limited. Of course, I'm saying IID, I'm replacing IID with exchangeability because we have to start from the simple situation and the simple questions before going to more generally. But a problem may not be, we might have time, data phenomena evolving over time, and the phenomenon might not be stationary, so we could have change points. We can have a COVID pandemic that breaks everything. And so I would say that statistics since ever have as prediction as a focus, but prediction now is an easy setting, is IID or exchangeable. But usually it's much more complicated, and statistics naturally deals with modeling stochastic processes that can behave in different ways in the future, not being stationary and so on, and evolve and have epidemics spreading. Apply probability, apply probability statistics. That's our quantifying the uncertainty. Statisticians are even too picky in this story of quantifying, providing credible intervals. Never provide only a point forecast. Okay, I stop because I chat too much.
Okay, the next question is also from Deborah. She says, some people believe machine learning is just a statistics that has been refined in a modernized way. What is your thought about this?
I think, and I tried to have the first apparently chatting slides on this. There is so much in common of statistics and machine learning. They have a lot in common. And in my 9 steps of a job of statistics, you could think yourself where you would put machine learning, your work, and statistics. And I'm trying to claim that Bayesian statistics is all over. But definitely, I have to say that machine learning has such an impact and such an energy in addressing complex models and technology. And so that we statisticians are not used to have. And instead, you jumped into all these problems and work in teams. And I think the basic questions, after all, are the 9 steps there.
All right.
But yeah, I think they have a lot in common, in fact.
All right. Laura is asking the question. It's actually extension of my question. So you were saying when P is exchangeable, there is a unique pair of model and prior law for the random direct measure, right?
Yes.
She's asking why that's the case. Maybe you could give us some, intuition. You cannot write here, so
yes, the intuition is that consider what is the model and what is the prior. So so you have think of the empirical distribution F hat n. The empirical, so you have 100 observation and build your histogram, and then you have 1,000 and you have a histogram, and you have 10,000 histogram. This histogram converges to a limit. And for any sequence of data, for any little omega, which means for any x1, x2 that you observe, for any sequence of data, that limit is unique. Why is it random? Because making the story a bit short, but intuitively, it's random because if I have another sequence, little omega, that limit may be different. That's peculiar of exchangeable data. It doesn't happen with IID. For IID, the limit is always the same, and it's the true distribution. So here we should comment further because it may be counterintuitive that instead, for an exchangeable process, depending on the sequence x1, x2 that I observe, I get to a different limit. That's why the limit is random. But it's a probability law. It's unique in the sense that as a random object is unique. And its probability law depends on the P that I have assigned on x1, x2. And so the limit is random and carries the distribution of the x that I generated. So the limit is random and has a probability law determined by the probability law of the x, which is what we usually call the prior, we call the limit a model, and the distribution on it, we call it the prior.
All right.
But it's determined by the fact that the model is, if you want, in a subjective, from a Bayesian subjective viewpoint, it's intuitive, because the probability is expressing my information.
Mm-hmm.
And so maybe there is a physically unique limit, but I don't know it.
Mm-hmm.
And so, okay, but that's a kind of simplistic explanation. Anyway, the model is the limit of the empirical frequencies. And so the empirical frequencies, what I observe, depends on the P I have on the X1, Xn.
Mm-hmm.
And that's why P uniquely determines the model and the prior.
All right, okay.
And in fact, what we are going, maybe it's worth to repeat this, it's not only the limit of the frequency, it's also the limit of the predictive distributions. It's a property, it's surprising, but it can be proved. Because the predictive depends on the empirical for exchangeable. So at the end, the predictive and the predictive and the frequency will converge to the same limit. If I see many data, my prediction will be the frequency, even for a Bayesian, if I in the limit. And so what we are going to do is we take an example of an algorithm, recursive algorithm, blah, blah. We take the limit, and that will be the model. And the model will be random with a prior. So we will have the prior, at least implicitly.
Okay.
Okay.
So we move to the lecture now, because
yes.
we have 40 minutes left.
Okay.
Do you want to try sharing your slides rather than sharing iPad? If there is a
let's see, share content. How can I share the slides?
So usually if you click share screen,
screen,
you can see different options. But I mean, if this is too stressful.
No, because I think I've been trying when I was doing the remote teaching. I guess I think it's this iPad that is not allowing me the same thing I would do with my Mac. But unfortunately, the audio of my Mac is broken, so I'll try to go on with the slides. Here, you are sharing your screen. Okay, but I can't see myself, which is very annoying. Okay, so that is the first part. Thank you very much for the questions, really. And so let's have an example of the problem of this example, unsupervised sequential learning and classification. That of course you teach me how to solve, but I'm addressing it through a simple mixer model. So the problem is we want to recursively classify observations into one of K groups, patterns, signals, with no feedback on previous classification. Okay, unsupervised learning and classification. We can do that in many ways, sophisticated, but now let's think we could to a simple finite mixture model where we have that Xn comes from one among K possible distributions, Fj. Here these distributions are known because we may know the distribution associated with a pattern or signals from previous data, previous experience. What we want to learn are the coefficients W's, the weights of these components, and we would like to classify the next observation Xn plus 1 in one of the appropriate component. What the Bayesian solution is in principle clear and simple. The unknown parameters here are the W's, so we assign a prior distribution, prior law to them. P of W, and then how is the problem of learning solved? Through the appropriate conditional distribution. So in this case, the posterior distribution of the weights given the data. How is classification solved? In this here is prediction. We compute the predictive probability that Xn plus 1 comes from the jth component given the data. What's the probability that the next observation comes from the jth pattern or signal? So in principle, the Bayesian solution is simple, but the computations get immediately involved. And the more so when we have streaming data, because of course we would need to update prediction and inference as a new observation becomes available. So even with batch data, the computations are complicated, the more so when the data arrives sequentially, and we want to do online sequential, online learning and classification. This is the problem we'll have in mind, but let me say that this problem with heterogeneous data is in fact common. It's a common classical problem that involves the case when we have different signals or patterns, or we have multiple experiments, for example, clinical studies in different hospitals, or we have different reactions, different parameters, different random effects on the individual response to therapy, and so on. So the problem is much more general than the final mixed model I just presented. For example, another example we can keep in mind, we may have clinical trials in different centers, Xi is the number of successes in center I, and we would say that the data are not IID because Xi, so the number of success in center I, is a binomial, but has a specific parameter, theta I, so the data could be independent, but certainly not identically distributed. And this is the case whenever we have a hierarchy of nested population groups, hospitals and units inside groups, patients inside hospitals, schools and students in the schools, genes in animals, and so on. In statistics, these kind of problems were the problems who gave rise to surprising results in the 1950s. Maximum likelihood was the method. Likelihood and maximum likelihood were the methods for inference, and instead there were no results by Stein or Kiefer and Wolfowitz were showing that the maximum likelihood estimator may fail having optimal properties in this kind of problems with, let me say, informally heterogeneous data. Instead, I think that beyond the principles, the foundational principles, and powerful features, and I say an advantage possibly of the Bayesian approach, is that it is quite natural and quite powerful in modeling heterogeneous data and complex dependent structures, even more complex like this one, using two other important, notions of conditional independence and hierarchical modeling. These are also two, important tools for a Bayesian statistician, particularly powerful in modeling those situations. We stay with a simple situation where we have just one level in the hierarchy. And now we say, suppose Xi is the response to a therapy, the average response to a therapy in hospital I. And we say, well, let's talk about individual. Xi is the response of individual I to some therapy. And so we treat theta I as random. So theta I is the random average expected response for individual I. And we say Xi given theta are independent. So patients possibly don't affect each other. It's not an infectious disease, but they are physically independent. But probabilistically, we say they are conditionally independent. If we knew the specific theta I, they would be independent. Otherwise, they bring information. So we use conditional independence. The theta I are random, and also they are considered here for simplicity as a sample from an unknown latent distribution G. But they are not IID, they are conditionally IID. If I knew G, then the theta I would be independent. And G is itself random, is unknown. So it's random. And remember, Bayesian approach, whatever there is, whenever there is something unknown for us, is random. We express our information on something that is unknown through probability. So is unknown, and we have a prior law. So here I have my artisanal picture of the hierarchical model. So we have a latent distribution G from which we sample the means, say, mean responses to a therapy of the patients. We sample the thetas, and then given the theta, we sample X1, the response for hospital for individual 1, X2, and so on. And again, let me underline that you see theta 1, let me say this is theta n minus 1 and minus 1, and here is theta n xn. So you see that the past thetas give me information on the latent distribution G, and through G, they give me information on the next theta n. So you see the thetas are not independent. They are a random sample, say, from G, but in Bayesian terms, they are not independent. They are exchangeable. And I can use information from the past to predict the next theta n. So here is the hierarchical model. It's important to notice that if we integrate out the thetas, then we are back to an exchangeable model, which is a mixture model. Oops. So the population, the distribution is a mixture with a latent distribution, a mixing distribution G. That we will be interested in estimating. Of course, it's a Bayesian approach. G is random. We give a prior on it. And in a way, we model G through the prior. Here is another very funny, So what kind of model, which is the other side of the prior? No? Prior and model is in a way the same word. No? So we could say, well, perhaps the response of patients to the therapy, these thetas are random sample from a Gaussian distribution, maybe with mean 0 and some variance. And then the variance is unknown. So we have a parametric model for the mixing distribution, and we give a prior on tau square. And then again, we have the hierarchical model. This model of the latent distribution is assuming that there is a 0 mean. Maybe this the response for the patient is the level of toxicity. So maybe we can think that across patients, we expect 0 toxicity with a variance. But we, you see, are modeling a sort of homogeneity among across patients. You know, we have deviations from the common value of the thetas, from the common mean 0. But we could think that the population is more heterogeneous. We may have a multimodal G density. And so we may think that the thetas are a sample from this multimodal distribution. And so we, in fact, have kind of 3 groups of patients where the toxicity is one level, another level on average. Or we could have a sort of extreme situation of this kind, where the groups are in fact, so you see these modes can be squeezed until they correspond to So this modes here, it can be more peaky until it corresponds to a point mass. And this means modeling the fact that we have three groups of patients. One has a value of theta, another, oops. Sorry. Whoop. Okay. And so we have this, we can model through the prior situation of presence of clusters or shrinkage effect and so on. So in fact, if we think of discrete mixing distribution, and in the last case here, then we are back to the finite mixture model that I mentioned for classification of patterns, say, and again, the solution would be clear. We give a prior on the weights, and then learning is solved through the posterior, classification through the predictive probability. But computations are involved. So we are back to that example. There is an extension of this classical finite mixture model where we don't know K, and we let K be unbounded. So we have a countable mixture. Countable mixture means that G, the latent distribution, is still discrete, but with a countable number of atoms. And we could say what is the prior we give. Well, to make the story shorter, we say that a popular prior on this latent G here, which is discrete, is a Dirichlet process. Now we just take in a way the limit of the finite dimensional Dirichlet distribution for K go to infinity with some reordering. Anyway, and you may have seen Dirichlet process mixture models, used in many applications because they model clusters, as the picture here was suggesting, trying to suggest in a short time. Maybe you heard about the Chinese restaurant process, that is the distribution of the clustering induced by the Dirichlet process prior on G. But it's not our point here. I'm saying again, I try to summarize these slides in the picture above, that G could be parametric, could be a normal, could be multimodal. So we can play in a way or think what is the most appropriate prior or model on the latent distribution. What I would like to underline is just that well, this is estimating G is not an easy problem. It's known to be a difficult problem because we want to estimate the distribution of the thetas, latent distribution, and the thetas cannot be observed. So it's more difficult than estimating the distribution, the density of the X that we can observe. Still, in principle, Bayesian inference is easy. We have just to assign a prior on G, and then inferences solved through the posterior distribution, the conditional distribution of interest. And in principle, the only trouble is that computations become involved. To see that become involved, I have here a couple of slides on how would be the computations for a Dirichlet process mixture model. If you want to listen, otherwise sleep a bit for a couple of slides, just to show that, if I assign to the G a Dirichlet process, which means G is discrete with infinitely many random atoms and random weights with some distributions on it, then if I could observe the thetas, the conditional distribution of G, given the thetas and the data, would be easy. Would just be a Dirichlet process centered that takes into account the frequencies. So in a way, I could look at this part here. You see that the point estimate of G would be a weighted average between a prior guess and the empirical distribution of the thetas. But I can't observe the thetas, so I have to take an average with respect to the posterior distribution of theta, and this becomes because I cannot observe the data, so I cannot say what these empirical frequencies are. I should compute the posterior of these data, and this becomes complicated because whenever I have a new observation, you see here, I revise. So I have to guess what's the frequency of the theta, what are the thetas. And so I have a posterior distribution on each theta. But whenever I have a new observation, you see I have n here, I update my information. I cannot do recursive computations here. Computations are going to be a nightmare. And so so in principle, the approach is easy, but oops, I'm struggling with this iPad. Oops, okay. And so how do we do computations? Analytic computations are difficult. We know that with batch data, so if we have n observation, we can use Markov chain Monte Carlo methods, which, however, are slow if we have big data. Or we could have variational Bayes. We could use variational Bayes approximations or approximate Bayes computations, ABC. But they wouldn't give us exact approximation. We know they are just approximations of the Bayesian solution, although they are amazingly useful, fast, and so on. But with streaming data, we need a sequential variance, development of MCMC or variational Bayes or ABC. Sequential version of MCMC, well, we know we have sequential Monte Carlo, particle filters in the context of state space models, but not so much as far as I know about sequential versions of variational Bayes. I know there exist, in fact, proposals of sequential versions of variational Bayes, perhaps not so much, to my knowledge, about sequential versions of ABC, that anyway are slow in the case of sequential Monte Carlo, often slow, at least with big sample size or complex data, although they could be exact, or they are just an approximation, or they are not clearly motivated. So people try to develop other algorithms that explicitly are an approximation of the Bayesian solution, and also are recursive. So I want to mention you about a recursive algorithm that is simple, fast, efficient, simple and fast. It's recursive. I can just update the previous forecast estimate when the new observation becomes available. But again, it's not clear what is the algorithm actually doing, in the sense that we would like to have an approximation of a Bayesian solution. Then we have some methods. We have this attractive fast algorithm, but is it an approximation of a Bayesian solution? And also we lose the property of the Bayesian solution, that is not only giving a point estimate or a point forecast, but describing the uncertainty through an entire conditional distribution. So the general question in this last part of the lecture is, somehow, can we go from algorithms to methods? Can I take an algorithm, read it in a statistical way, and read it as a statistical method, in the sense that I will explain in a moment. So this was our problem, classification, blah, blah. And we said more generally, we want to estimate the mixing density of a mixture model. And the data, for example, in binomial experiments, we have number of success that I is for the probability of success for patient I, and we want to estimate G, the mixing density, and the data arrive sequentially. So this recursive algorithm proposed by Michael Newton, in this literature is called Newton algorithm, but not Isaac Newton. So he proposes this algorithm, they propose this algorithm that starts at the prior guess and recursively compute an estimate. So I start from G0, and for each n, I consider an update. So this would be G0, G1, so step 1, this would be G0. And then I update my previous estimate that only depends on x1, xn minus 1. Update it with the posterior distribution that I would have using the previous estimate. See, it's Bayes rule. I have the likelihood, I have a new observation. I use the previous estimate gn minus 1 as the prior, and I have a posterior distribution of theta given incorporating the new observation using the previous estimate as the prior, with some coefficients alpha, some weights that usually are chosen like this. So I repeat this, and you see I recursively incorporate the new observation by just updating the previous estimate, incorporating the new, oh my God, my new observation. Sorry. Here we are. You rest while I struggle with the slides. So you see, this is the algorithm. So the algorithm provides an estimate of the mixing density for the problem of estimating the mixing densities in a mixture model. But so it is a stochastic approximation sequence, so you might be familiar with stochastic approximation methods. But it's not clear what the algorithm is actually doing. It's not, so you see, we abandon the idea, we just have a recipe. Take G0 and update it as incorporating recursively the new observation. What is this algorithm doing? Is it approximating a Bayesian solution? But also, what about uncertainty about the point estimate that it's provided by the algorithm? So people have been trying to, I go a bit quickly here, and more quickly, have tried to give an answer. Somebody looked at this just as a frequentist estimator and found frequentist properties. But what we would like to do is to show that taking a predictive approach, we can go from an algorithm, we can say something more about it. It's not just a recipe for providing a point estimate, an estimate of the mixing density. It comes from a Bayesian, approximately Bayesian method. In this sense, I will try to explain. So that's the algorithm again. You see, it's a sort of a recipe. Fast, quick, simple, at least in this fairly simple setting. I take the previous estimate and update it. But we want to understand what's going on in terms of, is there an implicit model? And can we quantify the uncertainty? So our trick, the key of our development is to frame the algorithm in a probabilistic setting. and to regard it as a probabilistic predictive rule. The PN, the predictive rule I was mentioning before. And then this way, oops. Why a predictive rule? Well, remember the mixture model. You remember there are these latent theta I. And for this model, you see, remember the hierarchical model here, the theta come from G. So we have this mixture. This is what we are estimating, or its density. We are estimating G, or the little g, the density. But this is a problem of estimation. Okay, oops, I'm sorry. Is the Bayesian point estimate in this case is the posterior expectation. So in principle, we would like a Bayesian estimate as the posterior distribution, as the posterior expectation. But the posterior expectation is also the predictive distribution of predictive probability of theta n plus 1 given the data. So when we say that an algorithm gives an estimate, well, the algorithm is giving the prediction, the predictive distribution of the next theta. And so if I look for a moment at this, that's more complicated than the basic exchangeable set I gave at the beginning, because here we have theta 1, theta 2, and then we also have x1, x2. But if I focus for a moment on this sequence, there is this interaction. I could look at the PN, the predicted distribution for this sequence. So I can regard the algorithm as a predictive distribution. And then, so what I do is say, okay, that's what I do. The algorithm gives a different predictive distribution. But then also in this setting, I can exploit what I was saying at the beginning, when we were fresh and not tired maybe as now. But, well, this predictive distribution now is interpreted, so it's not the estimate of the density, is interpreted as the predictive distribution of the next theta. And as such, it must imply an underlying model and an underlying prior. So we can exploit the approach I was mentioning, forget about this, and say what model. So suppose I take seriously the algorithm as my actual predictive rule. What model are we using? Well, here the data are not exchangeable, but they are such asymptotically. So this is what we can prove, that asymptotically there is a latent distribution G, and the thetas are a random sample from G. And then, and the Xi would be IID asymptotically as a mixture. So there is a quasi-Bayes mixture model. Why I say quasi or quasi in Italian, approximately Bayes mixture model, because this model holds only asymptotically. So for a finite sample, the algorithm is mixing a bit things up, but asymptotically we are back. So it underlies a Bayesian mixture model, an exchangeable Bayesian mixture model for n large. So here there was an idea of the proofs, which I was well aware I would have kept. I would be skipping, but I decided to leave this in the slides in case you are interested. And so now, but I tried to lead you here, to accompany you here. What we are going to do, we said that the model and the prior comes as limits of the predictive. The algorithm is giving me a predictive distribution. Okay, this setting of mixtures and the latent thetas is a bit more complicated, but the idea is the same. If I'm able to compute the limit and the probability law of the limit, that's my model, that's my prior. And this is what we do here. So I think I can jump to kind of the conclusions now that I want this little thing. Okay, yeah.
Sonia, sorry to interrupt.
Yeah.
We have about 5 minutes left.
5 minutes. Okay, I close by saying that giving all the solution, we can give credible intervals. So this answers the question about uncertainty. So the black line is the estimated, the estimate of the mixing, the latent distribution given by the algorithm, but we also have credible intervals, so uncertainty quantification like this. So to close, that's my summary. Well, let's see if we agree. I tried to claimed, and I think it's really a foundational concept, that prediction is central in Bayesian statistics and in machine learning. I tried to discuss, chat a bit on foundations, insisted on the predictive approach to move from the predictive law that in predictive rule that in principle characterizes the model and the prior. As an example, we looked at a simple mixture model. The example was Bayesian online learning and classification with streaming data. The computations are involved, and we said that the computations are involved, but then approximate solutions become attractive. Maybe they are not fully Bayesian, but they are fast. And we regarded the algorithm as a Bayesian probabilistic predictive rule. That was the key. And in this way, we at least we begin to have the intuition that we, taking the limit in the predictive rule, we can provide, we can understand what's the implicit model, we can in principle understand what's the implicit prior, and then compute the posterior distribution. So the algorithm would just give us a point estimate, the posterior expectation, but we have an entire distribution around it. So we can give an idea of the uncertainty about that estimate or forecast through credible intervals. So I mentioned this example, but I believe this approach can be interesting to explore for other predictive algorithms. And I thank you again. Thank you if you're listening from remote. And I thank the organizers. I thank Mi Zhong for chairing, and I hope to see you in some future meeting or future summer school. And then I feel very much old-fashioned. I said, maybe we'll meet at our summer school. That was this, planned for July, on the shores of the Lake of Como. Oh. And you see, what a pity. So Bernard Scholkoff was the first instructor of this summer school, goes back in the 1990s, but we have now a new place where we hold the summer school. Bernard was one of the first instructor of this in this new location, but I wasn't as good in having a remote summer school, and so I'm really, really impressed and amazed. But maybe in the future we'll have a summer school, or since you will be professors, maybe we will have a conference, and I hope to see you in person. And okay, email me if I don't manage to address questions during these days, and I'll be happy to stay in touch. Thank you very much.
Okay, thank you.
And I go back to
yeah. Yeah, your video. Okay. Yes. Thank you. So we have, so if you have any questions, please let us know, raise your hand or type this in the chat. So one question from Limor, how do hierarchical models relate to causal models in the per flavor or Bayesian networks for that matter?
That is, so in a way, the hierarchical model I presented is a kind of simple graphical model. And then we enter in the area of graphical models, which are fundamental for studying causality. So I don't see a straight relation with the kind of hierarchical models I was mentioning. So they were models for a hierarchical sample. stratified sample, I would say. I have schools and students in the schools, and I may have towns and schools in towns, in regions. So the hierarchy can be, but there is not an idea really of causality. This is more for a structured sample, hierarchical sampling. In causality, we look at dependence through the nodes in more with another vision, say. So you might know this long article in the Foundations and Trends in Machine Learning by Michael Jordan and Martin Wainwright. It's about 300 pages on graphical models, and I think there is also something on causality, and otherwise you have here people that can answer more specifically on the causality side, like Bernard and others. Yeah.
All right. Do we have more questions? Okay, if not, then let's thank the
Sonia?
Yes.
I have to tell that Sonia will have a roundtable after the break, so please join the roundtable as well if you have questions.
So there is one more question, and then I will have an announcement.
Yes.
For Bayesian inference, this is from Tan Tang. I'm sorry if I don't pronounce your name correctly. For Bayesian inference, could you comment on the pros and cons of the following method class? Sampling based, for instance, MCMC, optimization based, for instance, variational inference, and deterministic sampling, for instance, Stein variational inference.
Can I comment on this method as approximation methods? Yeah, too specific.
He wants.
I don't know if I heard the question properly.
Tan, do you want to ask her directly? Should we move this to
and computational aspects? Statistical and computational aspects of, for example, MCMC or so. So I think when we look at these approximation methods, in a way, it's more computational, no? I have the statistical answer, which is my nice conditional distribution, say, posterior the predictive, and then I need to approximate it. It's a purely computational method. Then I may use MCMC and go into beautiful probability theory of Markov chains, but that's another story. My aim is computations. So I have a predictive distribution, a Bayesian predictive distribution. I want to approximate it. And whatever method can be in principle as close as I like to the target, my distribution of interest, or faster, that's welcome. But then if I have streaming data, I need more. I need a method that I don't have to start from the beginning whenever I have a new observation. So I need sequential Monte Carlo also. So what I'm saying is that don't forget analytic approximation also, like asymptotic approximation, or algorithms like this one that is a stochastic approximation sequence. It's close to what is also used in empirical Bayes, but is not exact, is not one of the typical approximation like variational Bayes or ABC, but maybe also for those, or maybe also for ABC, say, I could say, okay, if the algorithm has the aim of approximating a prediction, a predictive distribution, that's why I'm saying predictive algorithm. Algorithm is giving me is trying to approximate a predictive distribution. Then I can take it seriously and say, okay, that's my predictive distribution. But I know that the predictive distribution implicitly comes from a model and a prior. And I want to be aware of what is the model I'm using. Also because if I do this, I can then quantify the uncertainty around the answer of the algorithm, which typically is a point estimate. Mm-hmm. So that was somehow the idea to be discussed. It works in the problem of mixtures. I don't know yet how far one can go.
All right.
Oh, thank you. Thank you to you for the question.
So Michelle is asking, are convergence results mostly based on weak convergence topology?
Yes, what the kind of convergence, like of the empirical, the predictive is weak convergence, and it also almost surely with respect to the P. So it's weak topology, but for now I take the opportunity for the problem we have, we could prove convergence in total variation. And if you are interested in Bayesian non-parametric inference, so what prior can we give to an unknown distribution? Okay, we have the Dirichlet process, we have others, but they are all discrete. And there is an interesting theorem that says that the prior we select a continuous distribution, absolutely continuous, say with respect to Lebesgue, only if the predictive distribution is absolutely continuous, it's a density, and it converges pointwise, so in other words, it converges in total variation to a density. So if it converges in total variation, then the limit will be also continuous. I have a continuous Pn, it converges pointwise, not only weakly, to a P, which will be my model, random, with a prior, so that prior we select. Anyway, the answer is, I take it back. The answer is yes, weak convergence. If we have a strong convergence in the sense of total variation, we can say more. Mm-hmm. That is perhaps a better answer.
So I will ask the last question. So this is from an anonymous attendee. I'm not sure if I got this right. Is the challenge of streaming data the change in the distribution that each data comes from, or simply the lack of data to estimate the distribution?
The story of streaming data I have in mind is just that I have the model, say, I have a task classifying signals into k possible different sources, and the data are coming sequentially. For patients in a hospital. So I have a first patient and I try to predict the toxicity of the therapy, and then a second patient arrives, and then a third patient, and then a fourth. Or I'm tracking a moving target, I'm tracking the position of Mi Zhong through her cell phone, but she keeps moving. In fact, no, she's always sitting in front of the screen. But if she moves, then I have new data and I have to track her position, updating my forecast of what her position will be. So that's the only meaning I meant to address. And of course, I need the temporal dynamics. I need to model a time series in this case because you're moving.
All right. So I guess let's thank the speaker again. A quick announcement is that we have 2 concurrent roundtable sessions at 4 p.m. One is with Sonia, the other one is with Peter Dayan. So you can choose either place.
Oh, but I didn't mean to be
no, we have roundtable sessions that are concurrently running.
Okay. Because I would very much be interested in the other.
You can also join him and then meet all together. Either way, yeah.
I don't know. You will have to explain me how to join the roundtable. Anyway, I will.
All right. Okay. Thank you. And see you later in about 22 minutes.
Okay. Thank you.
Bye-bye.
Ciao.
Bye.